text processing we take a few steps that we list out. So, we get the text which could be a text document or a micro text, which is a small text of few words. So, typically the first step that we do is, if we are getting text in a document, we generally try to clean up the document. In the cleanup process, we remove headers, footers and any other common formatting like page numbers, etc. After cleaning up the document, we are left with the main content of the document. So, what we do is, with this content, so we try to first tokenize the content. To take a concrete example, let us say we have a string everything that is not saved will be lost. So, by tokenizing, what we mean is, we want to break this string across the white spaces or tabs. So, here we get tokens like everything that is not saved will be and lost. So, the first operation is tokenization. After tokenization, we get individual tokens. So, these tokens are words, and we know that machine learning algorithms cannot work with words. So, we have to convert these words into numbers. So, we need to also see how to convert these words into numbers, and there are few schemes that are implemented in TensorFlow text package. So, second is convert words into numbers. Additionally, you might be interested in getting bigrams or in general n-grams from the token, from the string. So, the tokens are special case of n-gram, tokens are 1 grams. So, let us take an example. Here we have everything that is not saved will be lost as a string, and in order to get n-gram, we define first a sliding window of n tokens. So, for bigrams, for let us say unigrams or 1 grams, we have a sliding window of 1 token, and for each instance of a sliding window we record the token and then slide the window by 1 token. So, this is a second instance of a sliding window. then you have third instance, fourth instance, fifth, sixth, 8 instances. This is for unigram. For bigram, we have a sliding window of size 2, which we keep sliding one token at a time to get bigrams. Then we have for trigrams, we will define a sliding window of size 3 and so on. So, these are some of the pre-processing steps that we undertake for any of the text content. In addition to that, we use embedding to represent the tokens with numbers. Besides embedding, there are other methods like one hot encoding or a numeric representation based on mapping of the token to the string can also be used. Let us explore tf.text library provided by TensorFlow 2.0. The tf.text library provides a collection of classes related to text and operations that can be used readily with TensorFlow 2.0. The library can perform pre-processing that is regularly required for text based models, and it includes other features for sequence modeling not provided by TensorFlow, not provided by core TensorFlow. Most of the operation expect the strings are in UTF-8. If we are using different encoding, we can use transcode operation to transcode into UTF-8. We studied transcode operation a while back while exploring how to handle Unicode characters in TensorFlow. Let us take a string and encode it to UTF-8 16, and then we will use Unicode transcode to convert from UTF-16 to UTF-8. Given the line of text, the first operation is tokenization. Tokenization is the process of breaking up a strings into tokens. Commonly, these tokens are words, numbers and punctuations. The main interfaces are tokenizer and tokenizer with offset, which each have a single method called tokenize and tokenize with offsets respectively. There are multiple tokenizers available. Each of these implement tokenizer with offsets, which includes an option for getting byte offset into the original string. This allows the caller to know the bytes in the original string the token was created from, and this can also be used for variety of downstream analysis. All of the tokenizers return rack tensors with the innermost dimension of token mapping to the original individual strings. As a result, the resulting shape's rank is increased by 1. Let us look at the basic tokenizer, which is white space tokenizer. It splits UTF-8 strings on ICU defined white space characters such as space, tabs or new line. Let us see what kind of tokens we get with white space tokenizer on some of these examples, where we have one string which is in English, another string which has English word followed by an emoji, and both these strings are encoded in UTF-8, and we apply tokenize operation from the white space tokenizer. Let us print the list of tokens with tokens dot to underscore list. We can see that after we applied tokenizer, the first string got tokenized into words. The last token also includes a punctuation which is full stop. So, you can see that the first string got tokenized into everything not saved will be lost, and the second string got tokenized into a single token. So, there are 6 tokens in the first strings, there are 6 tokens in the first string and a single token in the second string. We can use more sophisticated Unicode strip tokenizer that splits UTF-8 strings based on Unicode script boundaries. So, let us look at how the strings get tokenized with Unicode script tokenizer. So, if you can compare these two outputs, you will see that the first string has now an additional token corresponding to the full stop, whereas the second string got tokenized into 2 tokens, one corresponding to sad and the second corresponding to the emoji. When tokenizing languages without white space to segment words, it is common to just split by characters, which can be accomplished using Unicode underscore split operation found in the TensorFlow core. So, let us try to split this Chinese string encoded into UTF-8. You can see that the strings the string got segmented into 4 tokens. Each token corresponds to a single character in the original string. When tokenizing strings, it is often desired to know where in the original string the token comes from. For this reason, each tokenizer which implements tokenizer with offsets has tokenize with offset method that returns the byte offset along with each of the token. Let us look at an example. So, you can see that tokenize with offset returns tokens, offset starts and offset limits. Offset starts list the byte, offset starts lists the bytes in the original string where the token starts. Offset underscore limits lists the bytes where each token ends. We can see that in everything not saved will be lost string, everything started with byte 0 and ended at 10th byte and so on. So, this way we can keep track of where the token started and ended in the original string. We can use tokenizers with tf.data API. Here we create a data set called docs from tensor slices with 2 strings, never tell me the odds and it is a trap. We use white space tokenizer on each string and we do that with a map method. So, in map what we do is we apply the tokenize operation on each of the strings. Let us look at the tokenized version of each of the strings in the data set. The tokenizer works as expected, just like it was working on the strings which were not included in the data set. After including the strings in the data set, and if we tokenize, we also get the same result. There are some other text operations that are also implemented in tf.text package. One of the commonly used feature is a word shape, where we are interested in checking if the string has a particular property. As an example, we want to know if the string starts with a capital letter, or if string has all the uppercase letters, or whether it has some punctuations or symbols. So, what we can do is we can tokenize a string and assess the word shape of each of the tokens. Let us run this to see the output. So, you can see that after tokenizing this particular string, and let us say after applying has title case word shape, you can see that this particular word shape is true for the first token, which is everything, and it is false everywhere else in the first string. In the second string, sad followed by emoji, it is true because it starts with a title case. None of the strings, none of the tokens in two strings are uppercase, that is why we have false everywhere. You can see that the last token, that is lost with a punctuation mark and sad with emoji, has some punctuations or symbol, that is why they are true here. None of the token is a number, that is why is numeric value is false. Finally, we want to sometimes convert the strings into n-grams. These n-grams could be, let us say, bigrams or trigrams, and the way we construct that is by defining a sliding window of the specific size. To give you an example, let us say, so everything not saved will be lost is, let us say, an example string, and let us say if we want to construct bigrams. So, since we are interested in constructing bigrams, n is equal to 2 in the context of n-gram. So, what we do is we define a sliding window of size 2. To begin with, position the window at the first token, and we record the bigram. We position a window containing 2 tokens and position it at the first token, and we record all the tokens that are in the window. So, the first instance we get everything not as a bigram. Then what we do is we slide the window by 1 token and position it to the next token. So, in this case we slide it by 1. So, now the window is positioned at the second token, and we write and we note down the bigrams that we get. So, here we have not saved as the second bigram. Then we again slide the window and record. So, we have saved will, then we have will be as the next bigram, and finally, we have be lost as the last bigram. So, we get 5 bigrams from the string. If we put n is equal to 3, we need to construct sliding window of size 3 and records the word and record the trigrams or 3 grams. So, here the 3 grams will be everything not saved, comma, not saved will, saved will be, and will be lost. So, there are 3 grams or 4 trigrams, each correspond to the position of a sliding window of size 3 across every token. So, you can see the text.ngram where we set n is equal to 2 and we get bigram by using the reduction type of string join. So, we got the bigram as we listed in, we got the bigram same as the ones that we worked out, and in case of the second string sad, it is a single token string. So, there are no bigrams. So, it is empty.